Hello, everyone. This is Barbara Bridges. I am the director of Art to Change the World. We do social justice projects, and you don't necessarily have to be an artist to participate in one of our projects. So I'm here today with Neil Granlund, who we hired to be the scientist in a project that we did for the Mississippi Watershed and Management Organization. We got a grant from them to look at what is left in the Mississippi, do an analysis on it, and create an elegant artwork. So do you think we met our goal, Neil?
I do. Yeah, we definitely pulled a lot out of the river and used quite a bit to make this piece.
So this was your first experience at art making, I understand. Is that correct?
Yeah, it was.
So what did you think from the beginning? What was your reaction, and then at the end?
At the beginning, I really had no idea what we were going to do with everything that we pulled out. It's really not my forte, to make found art. When we first pulled everything, I was like, oh my goodness, I have no idea, how we're going to shape this into something that'll look like the beautiful piece of art that we ended up making. So I was a little apprehensive at first, but I knew I was in good hands because I was surrounded by 8 other people who have done this quite a bit in the past, and so I figured I'd follow along and learn along the way.
Okay, well, let's go see this piece and see what happened. So we made what we ended up naming the Mississippi River Pearl. And everything in this artwork was found on the river by our 9 participants in a 2-hour session, except for the chair and the cabinet, which were also recovered and recycled. So there's the front, there's the back. This is 21 inquiry drawers, and I'm really proud of how much fun we had designing the fronts and the contents of these drawers. And so we used the presentation that you're going to hear shortly from Neil, and made art and did research and found out just exactly what goes in that river and how it affects us. I think it's important for you to see the kind of community that was built as we created this work. The person who, river keepers, took us out on the boat to do the west side of the river. When I spied this white thing, he said, "What? You want to go get that?" This is the front of a car bumper. Here's the cabinet in progress. And you can see we had a lot of fun. We put our best clothes on, of course, to create this object. And here are some of the candid shots as we made it. I think it's also important for you to see some close-ups. Frances Bates did this little installation of all the fishing things she found. Lucy Schroffner, who is an incredible artist in fabric, created this seat covering out of the fabrics we found. We used a pair of jeans to put our cards in. And here are some small works created by the participants to show the special things that they found. This was something that I made right here, and that was my favorite thing, that little toy that I found. So I made him a little seat that he could sit on. And the wings are the plastic bottles, the clear plastic bottles that we found. So with no further ado, I'm going to turn this over to Neil, who is going to share his research with you. And I think you're going to find it just as fascinating as we did.
All right. Here we go. All right. So when Barbara first approached me about doing this project, she was looking for someone in the polymer sciences who knew a lot about polymers. And I'm definitely that person. I work for a company by the name of Stewardship. I've worked with polymers for, I want to say, probably about, I don't know, 16 years, something like that. Pretty much since I got into the industry. I was working with polymer related projects. So at 3M, went to a small company for a while, and then ended up at Stratosys. And so here's what I had to share with my group. We went out and collected some things on the Mississippi, and I gave this presentation to kind of allow them to learn a little bit more about plastics themselves and about the types of materials that we found. So the topics I covered were, the introduction to plastics, how to identify polymers, how do they affect our environment, and polymers amongst the materials that we collected. So in the introduction here, not a lot of people know precisely what polymers are made of, but they're made from additions of many monomers through a process called polymerization. So monomers are really small molecules. They just have one repeat unit, but through we call polymerization, you can make polymers, which are very large molecules. Whenever I talk to friends and family about what a polymer is, but specifically, I like to break it down and say that a good analogy is to think of polymers as or a monomer as one Lego block, and polymers are many blocks put together. Only instead of this small stack we see in the presentation here, the blocks of polymers that you would have together would be in the thousands or millions to make that one polymer. There's a difference between the different types of polymers that you see. There's two basic ones, is thermoplastics and thermosets. Thermoplastics are what we use most often, in our everyday lives, like bottles and trays and those types of things. These plastics will soften when they're heated, and they can be reformed and turned into other things. A really good example of a thermoplastic is an ABS Lego block. So we could take that Lego block, we could chop it up, we could heat it up, and we could turn it into another Lego block. The other type of polymer that we see sometimes in our lives is our thermosets. Thermosets contain a network of permanently tied together bonds. And that happens in a curing process known as cross-linking. This sets the molecules into place, and those polymers can no longer be remelted. The example I've got here is a scorpion, in the epoxy resin. If we wanted to get that scorpion out, we would have to physically break that block or burn it to the point where we would get at the scorpion. There's no just melting that out of there any longer. A little more on thermoplastics and thermosets to kind of give you an idea of what they look like. Thermoplastics are best envisioned as cooked spaghetti. It's a solid mass tangled up into a random mass of coils. And you can think of them a lot like a spaghetti in water. You can take an individual molecule out, right? Or a long chain. But thermosets are best envisioned as a large net. They are stuck together to each other. So you couldn't take just one random string out. If you tried to pull it, you'd get the entire net. You'd pull the entire net. So a lot of people ask, where do polymers even come from? And a lot of people don't know that nearly all plastics come from oil. Crude oil is a big mixture of a whole bunch of different types of molecules. And so what we do is we heat it up, and through distillation columns, we capture various lengths and various types of molecules, which can be used as the building blocks for polymers. Some polymers are bio-based, though. There's a type of polymer that's made from castor oil. It's a nylon 11. It can be made by both oil or castor oil. But castor oil comes from the castor bean and can be grown, extracted, and then turned into a plastic. PLA, otherwise known as polylactic acid, is produced from corn. They grow corn, they get the lactic acid out of it, and they do a polymerization process. And so that's a bio-renewable source of plastic for us. Sometimes you'll see those as very clear, like I think they call them clamshell containers in the grocery store. So on occasion, those will be made from PLA. And even polypropylene, the stuff that you would find in like your Gladware, can be produced from sugarcane. That's a biorenewable source, but not a biodegradable source. So as I mentioned here, there is a big difference between biorenewable and biodegradable. How do we identify polymers? So for the scope of this project, not everyone in this group was obviously a scientist. I was working with a lot of artists. So I identified a couple of different ways for people to determine what it is that they were working with, right? And the first one's the easy way. The easy way is basically take a look at what you pulled out of the river and see if there's what we call a chasing arrow on it to determine what the polymer may be. So a lot of plastics that we buy in the stores have the chasing arrow recycling symbol on them. The chart on the right here shows the 6 most commonly recycled plastics. And I say 6, even though it shows 7, because the 7 numbered plastics are rarely recyclable. Those are typically just thrown away at the recycling facility. These plastics, as you may have guessed, are frequently used and therefore the most common ones that you'll find in our rivers, lakes, and oceans. So that's the easy way. But if you can't find a chasing arrow, there's the hard way. So for the hard way, if you can't find a recycling symbol because it's missing or the plastic's old and faded or it just doesn't have one, then you have to use analytical techniques. And that's when you need to have a scientist friend, such as myself. 3 commonly used techniques that we have in the plastics industry are DSE, which is called differential scanning calorimetry, or FTIR, which is Fourier transform infrared spectroscopy, or NMR, which is nuclear magnetic resonance spectroscopy. Don't worry about learning those terms. These are just things that I deal with, on a pretty frequent basis. And these are the things that I use in order to identify plastics in case I have something that I don't know what it is. The information that you receive with these tests, plus a good reference such as MatWeb or UL Prospector, will give you enough information to determine what those types of polymers are. So I broke down, some of these techniques here. So for DSE, basically what we're looking at is you've got a couple of different pans. One has your sample in it. One is a reference pan. They're both heated up at the same time, and the amount of heat required to increase the temperature in the pans is measured. And based on how one heats up compared to the next, it gives you certain properties of the polymer, and that's how you can determine what it is. For FTIR, basically we shoot a sample with different wavelengths of light, and then we can determine how much light is determined at different wavelengths, and that will give us the functional groups that you see on a polymer. This technique can be used for solids, gases, and liquids. You just have to have different setups. And I already mentioned that the different absorptions will reveal different structures of the matter that you're looking at. And lastly, and one of the best techniques actually for taking a look at polymers is NMR. This technique uses local magnetic fields around atomic nuclei. Basically, you hit it with a big magnet, and a controlled magnetic field reveals which electrons are within the molecular structure, giving you a complete view of what the polymer looks like. This technique is very commonly used in organic chemistry. It gives a complete picture, which is really nice. Something I don't have access to myself because we don't make polymers here. We pretty much know what we're working with on a regular basis, and it's an expensive machine. So one thing that we were concerned about, and that my group had a lot of questions about was, how do polymers affect our environment? And so I wanted to get into that a little bit as well. Due to the fact that plastics can't be broken down, obviously they stay in our environment for a long time. Plastics are found where no humans have ever been, actually. There's a remote island called Henderson, and it's a tiny uninhibited coral atoll in the middle of the Pacific. And plastic has been found on that island, and also at the bottom of Challenger Deep, which is the deepest part of the Mariana Trench. There's a plastic bag found down there. And how does it get there? Well, nearly all the plastics in our oceans come from our rivers. It's not from intentional dumping, as a lot of people think. You just can't dump that much in. And it's not from accidental spills when shipping materials across the ocean either. Essentially, what's happening is that, I think I covered that here. Yep. So how do they get there? So in a 2017 study in Environmental Science and Technology, which is a magazine, they concluded that the 10 biggest rivers contribute about 90% of all the plastic waste in the ocean. That didn't seem quite right, though. So another group of people from Science Advances magazine did a study just last year in 2021 and really determined that it was over 1,000 different rivers that contribute about 80% of the plastic emissions into our oceans. And really, the severity of those emissions are based on how close the rivers are located to large populated areas that have a lot of waste and not a lot of great sanitation, taking that away and putting it into a landfill, which makes Southeast Asia, the Philippines, Indonesia, and the Dominican Republic some of the largest sources of plastic pollution in our oceans. A lot of people think that plastics, leak toxins into our foods when we use them. What's in our bottles, what's leaking into our food as we heat it up in the microwave. Well, in reality, not much. While it's true that there are some specialty materials that contain flame retardants, heavy metals, and pollutants, and those types of things, the majority of the common plastics we use are bottles and packaging, and they don't have those types of additives in them. If you talk about high density, for example, this is what our milk comes in, high density jugs. It consists of ethylene monomer polymerized in a solvent, benzene most likely. And ethylene itself is a gas with a boiling point of negative 150 Fahrenheit. And benzene is a liquid with a boiling point of 176 Fahrenheit. So when you do the polymerization of that material, you turn it into a large HDPE molecule, and then it goes through a catalyst composition step, goes through a drying step to remove the solvent or the benzene, and then it's extruded at 390 Fahrenheit, which is way above both of the boiling points of those two materials. So all you're left with in the end is high density polyethylene. There's no ethylene left in there. There's no benzene left in there to leach into your foods. And while it's true that most virgin plastics, it's possible for plastics in our environment to absorb heavy metals and harmful organic compounds in pharmaceuticals. They essentially act like sponges. So once they're out in the environment, they can take in, toxic materials. According to current estimates, about 0.8 to 2.7 million tons of plastics are being dumped into our oceans each year, and we don't know what they're pulling with them along the way. And if that's an accurate measurement, the mass of plastic will exceed the mass of the fish that live in our oceans by 2050, which is a really sad statistic. Hopefully that never becomes true, but time will tell. But in summary, the biggest threat to our oceans is the amount of plastic that's going into it, not necessarily the toxins that are being leached out of them. And that has a negative impact on all ocean life. All right, and then getting to the materials that we actually pulled out, Barbara asked me to analyze a few different things that she set aside and said, hey, why don't we take a look at these specifically and find out what they are? Plastics chemist. And I was like, sounds good. I'll take that to my lab and we'll do a little bit of analytical technique or testing on those materials. So the one thing that I have available, or the two things that I have available that I mentioned earlier, are DSC and FTIR. Because these are really common plastics, I knew I could get away with just looking at the DSC to identify these materials, because I figured they would be polypropylene, high density, polyethylene terephthalate or PET, those types of things. And so they would be rather easy for myself to identify. So I only used DSC. So one of the materials that we had was a green cap. This green cap was identified by me as being the top of one of those lemonade caps that you typically get at like the carnival or something like that, or at the fair. Here we have the DSC of that. And based on the peaks that I saw, I determined this was high density. Another one was pop bottle. This was an easy one to identify because this is one of those materials where we could go the easy way and determine what the material was. Just look at the chasing arrow and find out it was PET. But I analyzed it regardless, and I found that the characteristics of the material itself are consistent with PET. So that's what it was. We found a coat hanger when we were out and about. This one, when I saw it, I assumed it was just going to be a mix of maybe high density and low density polyethylene materials. But as it turns out, I was surprised that it was a mix of polypropylene and HDPE, or high density polyethylene. And I could tell that because of the two different peaks that I saw in the initial melt. The last one, or no, the second to last here is the foam block. We found a lot of polystyrene when we were out. It's pretty characteristic by the fact that it's a light, block with a lot of small little granules in it. But I took a look at it via DSC, and I found that it has what's known as a class transition at 97C. And that's exactly what you would find in polystyrene. And so given the fact that it was lightweight and it also had a characteristic property of polystyrene, determined that that was polystyrene. And last but not least, we had an inner tube that we had found from a bike. As you can see in this scan, there's really not much of anything to look at here. There's really not a whole lot of transitions that pop out at me. So this one was really difficult to positively identify as anything that I could find using analytical techniques. So essentially, we ended up identifying this one just by kind of looking up what inner tubes are made of on the internet. So, but this would be a difficult one if someone were to give it to me and just say, hey, Neil, can you identify what this is? If it was just a small little piece without knowing that it was actually an inner tube. And that was the presentation.
Thank you so much, Neil. It was very interesting because you busted some myths about specifically the microwave thing. We were all surprised about that. And then, of course, horrified that there are these islands of floating plastic out there. Right. What was it, the size of Connecticut, one of them, or what was that?
2 times the size of Texas.
Oh my gosh.
Two Texases put together. Yeah.
Yeah. So that is pretty amazing. So Again, this project was funded by the Mississippi Watershed and Management Organization and executed by Art to Change the World. Our next project that I'm thinking about is looking at the 13 lakes in the Minneapolis city limits. So we're going to be looking for 13 people. Each one is going to adopt a lake and develop a whole project, however they envision it around that. So if you're interested in getting involved, reach out to arttochangetheworld.org. Thank you for your time, Neil.
You bet. My pleasure.